So we were doing EM induction cfqs. Okay, so in problem number 11, it is a problem of mutual inductance. A circular current loop is given. Okay, of radius r, and you need to calculate the mutual flux through a square loop of side A, which is at an angle of 45 degree. Okay, now first let us calculate, this distance is root 3r. First let us calculate the magnetic field at an axial point. So it is mu naught ni r square by 2 r square plus x square to the power 3 by 2. So it will be mu naught. Now there are two terms, 2 I r square by 2 r square plus 3 r square to the power 3 by 2. Now it is 2 and 2 gone, so it is mu naught I r square by 4 r square. So the root is 2r, 8r cube, the cube. Okay, so it would become mu naught I by 8r. Okay, now let us calculate the mutual flux, that is B A cos theta, cos 45 degree. So it is mu naught I by 8r A will be a square and this will be 1 by root 2. So mutual inductance will become mu naught by 8 root 2 a square by r. So from here the expression is given, and from the comparing it with the expression, we can write 2 to the power p by 2 is 8 root 2. So it is 2 to the power 3 plus half, that is 7 by 2. So clearly p is 7. Alright, now let's do problem number 12. Okay, this is a very conventional problem. So we have two resistances, the equivalent resistance in parallel, these two resistances 1 by 4 and 1 by 12. So it would become one by 3. So R equivalent is 3. So the current I will be epsilon by R equivalent plus small r. So it is BLV by 3 plus small r is 2. So it is 0.5 into L and V. Here L is 0.25 meters and velocity is 4 meter per second. So it will be 0.25 into 4 by 5. So it will be 1. So it is 0.1 ampere, the induced current. Now let us do problem number 13. It is given, this is a very important CFQ. A rod of length L, conducting rod, is moving with a non-uniform velocity. Suppose the velocity at this end is V1 and this end is V2. It's not the entire rod is moving with V, right? Then the induced EMF. Okay. So how can we calculate it? So first let us take a distance x. Take dx, a length. So the induced EMF here will be given by B. L is dx into V, right? So the velocity of this element dx is V. Fine. Okay. So see, the change in velocity in length L is V2 minus V1. Okay. Velocity is changing from V1 to V2, from this end to this end, that is over the length L. So per unit length the change in velocity is this. Okay. So in x length the change in velocity will be into x. So the velocity at this end is V1. So what will be the velocity at this point? That is, what will be V? V will be V1 plus this change V2 minus V1 by L into x. Okay. Fine. So it will be d epsilon is B dx. Now this is V1 plus V2 minus V1 by L into x. Okay. So what we can write is epsilon will be B V1 integral dx from 0 to L. Okay. Plus B V2 minus V1 by L x dx. Alright. From 0 to L. So it will be B V1L plus B V2 minus V1 by L into L square by 2, right? So it will be B V1L plus B V2 minus V1 L by 2. So it will be B L common V1 plus V2 minus V1 by 2. So it will be half B, this is V1 plus V2 by 2, right? So V1 plus V2 into L. Okay, fine. So it is basically coming out to be B V average into L, right? Isn't it? Okay, for this rod. Okay. When the two ends are moving with two different velocities, the induced EMF can be calculated as this. Okay, this is a very important question they ask you. now the 14. It is very elemental. Simple Faraday's law. Okay. So epsilon is minus d phi dt. So you just do it minus d dt of phi, that is b into area. Area will be b square of the square loop into what you will write, cos theta, right? ba cos theta. Okay. So it will be b square cos theta will be minus sin theta minus minus plus sin theta into d theta by dt. Okay. So it will be b square, d theta by dt is omega sin theta. Theta can be written as omega t. Okay. So it will be given like this. Okay. Okay, so now 15, again a very important question, cfq. Okay. A conducting rod has been bent like this. Okay, and it is moving along the angle bisector with velocity v. Okay, so this total angle is theta. So this angle is theta by 2 and this is theta by 2. The total angle is theta. Now how we will calculate it? Let this be L and L. Okay, what is the induced EMF? Okay, you can calculate it in two ways. Okay, one way to calculate it is the simple BVL method. Okay, so you tell me one thing. In the conventional case, here is the magnetic field is like this. Okay, in the conventional case, what you have studied, in this type magnetic field, a conducting rod is moving like this with velocity v. Okay, so epsilon becomes BLV. Alright, you have seen. Okay, so the magnetic field is perpendicular to the plane here and here also. So nothing to worry about the magnetic field. What is important is the conducting rod here is moving perpendicular to the length, right? Okay, but here if you consider this length, the conducting rod is not moving perpendicular to it. Okay, fine. So you need to calculate the perpendicular length. Okay, fine. So if you join this one, join this length, okay, and this much also. Okay, so this is L, okay. So you see the perpendicular length here is coming out to be, now this becomes L sin theta by 2, right? This length becomes L sin theta by 2. Okay, and this also L sin theta by 2. Fine. Now you see this rod is moving, if you consider this red colored rod, then the velocity of this rod is perpendicular to the length, like in the conventional case. Okay, clear? So here now you can consider that it is the EMF will be B and the length is 2L sin theta by 2 into V, BLV. Alright, clear? So here this will be the BVL sin theta by 2. the induced EMF across the rod. Okay, fine. Also you can take the components of V. Okay, the component of V perpendicular to the length. The similar thing will happen. You see, if you I'm using different color to denote. See, if you take the components of V along the length, then it becomes V cos theta by 2, and perpendicular to the length, then it becomes, see, V sin theta by 2. Okay. Okay, if this is your V, right? Clear? Okay. So obviously you don't have to take this thing which is along the length. You have to consider the velocity component which is perpendicular to the length. Okay, V sin theta by 2. Then also you will L into V sin theta by 2, okay, into B. Say BVL sin theta by 2 is the EMF of one half of the rod. EMF developed in one half of the rod. In the another half it is again BVL2 sin theta by 2. So the total thing will become 2 BVL sin theta by 2. Okay, you can think like this. Okay, and another way of doing this problem is the flux cut problem. Okay, আমি তোমাদের বলেছিলাম ফ্লাক্স কাট প্রবলেমটা, যে ধরো এরকম রয়েছে কন্ডাক্টরটা, তাহলে ফ্লাক্স কাট প্রবলেমটা কী করে করতে হয়, এই কন্ডাক্টরটা কিছুক্ষণ পরে ধরো এখানটায় চলে গেল। ওকে, তাহলে আমাদের কি করতে হয়, এর ইনিশিয়াল আর ফাইনাল পজিশনটা অ্যাড করতে হয়, রাইট? সো আমরা ইনিশিয়াল অ্যান্ড ফাইনাল পজিশনটা অ্যাড করছি। ক্লিয়ার? ওকে, ফাইন। তাহলে এই যে এরিয়াটুকু, ক্লিয়ার? ওকে, ইনিশিয়াল আর ফাইনাল পজিশনের মধ্যে যে এরিয়াটুকু, এই এরিয়াটুকু দিয়ে যে ম্যাগনেটিক ফ্লাক্স পাস করবে সেটাই হচ্ছে চেঞ্জ ইন ফ্লাক্স, রাইট? তাহলে হাউ টু ক্যালকুলেট দিস এরিয়া? আচ্ছা, ইফ আই কনসিডার this, if I consider this rectangle, okay, this rectangle has the same area of this much area, because you see, if you cut this area and put it in this blank space, then you will cover this one, okay, and you will get this rectangle, right? Clear? Okay, if you cut this triangle and you put it in this blank space, then this will be filled up, this triangle will be filled up by this triangle, so you will get this rectangle, right? Fine. So this area, this much area, shaded area, is basically the area of this rectangle, right? Okay, so what will be the area of the rectangle? Say in time t it is moving with velocity v, right? So in time t it moves vt. Okay, and as I said, this is L, so it is sin, it is theta by 2, it is theta by 2, so this length is clearly L sin theta by 2, this length. Okay, now what is the area of this rectangle? 2L sin theta by 2 into Vt. Okay, area. So if you multiply it with B, so B into this area is the change in flux. Okay, d5. Okay, so do it in time dt, right? It's better to do time dt. Okay, so it is v dt. So what is d phi dt? d phi dt is 2 BLV 2 BLV sine theta by 2. Okay, this result. This is epsilon, Faraday's law. Okay, so this is flux cut. Already I have taught you this thing, flux cut. So you can do it either by the method of flux cut or by the conventional method like this. Okay, so always remember this thing. This is epsilon is BLV perpendicular, that is the perpendicular component of velocity with the length. This velocity, you have to take the velocity component which is perpendicular to the length of the rod. Okay, fine. Now 16. So here IT curve is given. It is like this, this and this. This T by 4, T by 2 and this is 3T by 4. Okay. So in the first case it is I is KT. The equation, a straight line passing through origin. So di dt will obviously be K. So epsilon is minus L di dt. So it will be minus Lk. Okay, so it's a constant, and then I is constant, so di dt is 0. That means obviously EMF will also be 0. And in the third case it is a straight line with a negative slope, so it will be I is like C minus KT. So di dt will become minus K, right? So epsilon will become plus Lk. Okay, from epsilon is minus L di dt, it will become plus Lk. So it's a positive constant. Okay, so epsilon versus T graph will be very easy. So first it is negative, then it is 0, then it is positive. Okay, clear? So it is 0 to T by 4, it will be up to 0 to T by 4, then it is up to T by 4 to 3T by 2, then from T by 2 to 3T by 4. Okay, clear? So graph will be like this. A similar thing they can give you with a magnetic field versus time BT graph. Okay, here also is B is KT, so dB dt is K. Okay, so if you consider phi, epsilon is minus d phi dt, so it is minus d dt of BA, so epsilon will becomes minus A dB dt. so it is minus ak. Okay, so for this graph the epsilon versus t graph will be like this. It's negative and constant like this. Okay, fine. Alright, for bt graph. Alright, 17. Is given t square e to the power minus t, the current. So di dt will be 2t to the power minus t plus, or rather it will become minus t square e to the power minus t. So take t to the power minus t common, so it would become 2 minus t. So EMF will be minus L di dt. Okay, so when EMF will become 0, then di dt also becoming 0. So it is two minus t is becoming 0, because this thing cannot be 0 for any instant t. So t equals 2 seconds. Okay, so at 2 seconds epsilon is becoming 0. Okay, fine. So now let us do 18. Here in a magnetic field, a semicircular ring is rotating like this. Okay, at some instant it is making an angle alpha, theta. So at the next instant, suppose the ring further rotates by an angle d theta. Okay, so now this becomes the ring. Okay, it further rotates. Okay, so how much area is increased? How much more area is entering the field? This much. Acha, what is this angle? This angle is d theta. If this is d theta, this arc length is r d theta. Now actually see, this is basically a triangle. Okay, now what is the area of this triangle? R base and height is r d theta. So the area of this triangle is dA is half r into r d theta, that is half r square d theta, right? So what is dA dt? It will be half r square d theta by dt, that is omega. So it is half r square omega. So what will be phi? It will be call it directly, do it epsilon minus d phi dt. So this is minus d dt of b into a So it is minus b dA dt. So it is minus half omega b r square. Alright, clear? If you want to take the magnitude, the minus indicates back EMF, you can take it. Okay, the magnitude is only, the value is half omega b r square. Okay, now if the ring is rotating with acceleration, okay, I have done this problem, it is rotating with uniform angular velocity omega. Okay, now if it is rotating with acceleration, what it will be? Okay, now see, suppose it is rotating with an angular acceleration alpha, then at time t, theta will become half alpha t square, isn't it? You know the kinematical equation from class 11. Okay, theta is half alpha t square. Okay, so here d theta dt will be, so omega, directly we can write it na, alpha t. Okay, so then it will be half r square alpha t. Okay, so it will be directly epsilon will be minus half, in place of omega we will put alpha t, so alpha b r t. Okay, fine. So here EMF is proportional to t, directly proportional to t. Here EMF is independent of time if it is moving with uniform angular velocity. If it is moving with uniform angular acceleration, then the EMF will be proportional to time. Okay, fine. Okay. Again you see, when it will move from 0 to pi by 0 to pi, okay, from 0 to pi, okay, within that period EMF will be negative. Then when it will be pi to minus 2 pi, then EMF will be again positive. Okay, clear? Fine. Okay, so can you get this thing? Oh sorry, here it is r square. Okay, b r square, okay. So can you get this thing, what I have told, that EMF will once be from 0 to pi, okay, as this loop is rotating from 0 to pi, EMF will once be negative, and from pi to 2 pi EMF will again be positive, like this. Why? Okay, again from 2 pi to 3 pi it will be negative. Why? Because you see, if this, when from 0 to pi, this entire loop is entering the magnetic field gradually. That means magnetic flux is increasing through the loop. Okay, so magnetic flux is increasing, so accordingly, as per Lenge's law, induced EMF will be produced. But when it will be 0 to pi, when this loop has been rotated by an angle pi, the entire loop has entered the magnetic field. So magnetic field and magnetic flux I should say properly. So as this loop has been rotated by an angle pi from 0 to pi, magnetic flux is maximum through the loop. The entire loop has entered the magnetic field. Now from pi to 2 pi, actually now this loop is getting out of the magnetic field. You have to imagine. Okay, you have to visualize. Okay, from 0 to pi it is entering, and from pi to 2 pi it is exiting the magnetic field. So magnetic flux is decreasing. So accordingly as per Lenge's law, the EMF will be induced in the opposite direction, opposite to the previous case. Okay, so once if you consider the induced EMF to be negative, the next time it has to be, you have to consider it to be positive. Then again it's negative and positive, alternately it will go on like this. Okay, as this loop will go on rotating. Okay, মানে the thing is very simple. লুপটা একবার ম্যাগনেটিক ফিল্ডে পুরো ঢুকে যাবে, আবার ম্যাগনেটিক ফিল্ড থেকে পুরো বেরিয়ে আসবে। তার মানে একবার ম্যাগনেটিক ফ্লাক্স 0 থেকে আস্তে আস্তে বেড়ে ম্যাক্সিমাম হয়ে যাবে, আর একবার ম্যাগনেটিক ফ্লাক্স ম্যাক্সিমাম থেকে আস্তে আস্তে কমে 0 হয়ে যাবে। সো 0 থেকে যখন বেড়ে ম্যাক্সিমাম হবে তখন ইএমএফটা যা, আর ম্যাক্সিমাম থেকে কমে যখন 0 হবে তখন ইএমএফটা ঠিক তার অপোজিট পোলারিটিতে থাকবে। তাহলে একটা নেগেটিভ হলে একটা পজিটিভ। ওকে, সো অবভিয়াসলি এরকমভাবে টাইমের সাথে এইভাবে ভ্যারি করবে দ্য ইনডিউসড ইএমএফ। ঠিক আছে, ক্লিয়ার? ফাইন, এইভাবে বুঝতে হবে। ফাইন, ওকে, ঠিক আছে। Alpha is the angular acceleration. Okay, so these two cases, very important CFQ this one is. Okay, they can ask you to draw a graph, variation of the EMF with time. Then number 19 is dimensional formula of phi and L, magnetic flux. Acha, first magnetic field, dimension of magnetic field is always easy to calculate magnetic field from this equation, F equals QVB. Okay, or bill also you can use, BIL. Okay, so it is use bill. Okay, the same thing. Okay, so it is ML t to the power minus 2 B, this is AL, so B is, L is gone, so it will be M A to the power minus 1 T to the power minus 2. Okay, all right. So magnetic flux will be B into A, that is BL square. So it will be M L square A to the power minus 1 T to the power minus 2. This is the dimensional formula. Okay, and they have given you to calculate the dimensional formula of self inductance, L. It's always easy to calculate L from U is half Li square. Okay, so this is ml square T to the power minus 2, and this is half this self inductance L. Okay, do not consider it to be length. Okay, and I, that means A square. So half you do not have to write in the dimensional equation, it's a constant. So it will be, the dimensional formula of L will be M L square A to the power minus 2 T to the power minus 2. Okay, it's like this. Okay, so now the last question, 20. It is the very conventional question. Already we have done many types of this question. Actually this type is very important in EM induction problems, among the EM induction problems. So it's a falling rod, it has a mass m, so it has a weight mg, it's falling under gravity and in the magnetic field. Okay, it is the same problem that I have discussed in the class. Suppose an experimental demonstration supposed to be demonstrated at the class of your school. Okay, then a coil is there, okay, and a bar magnet is falling through it. Okay, fine. So the bar magnet slows down. Okay, I've already discussed this thing in the class. Okay, what will be the direction of current when the bar magnet is entering the loop? Okay, what will be the direction of current when the bar magnet is exiting the loop coil? Okay, সো কয়েলে ঢোকার সময় কী হবে, বেরোনোর সময় কী হবে, আর কয়েলের মধ্যে দিয়ে চলার সময় কী হবে, অলরেডি ডিসকাস দিস থিং। অ্যান্ড এটাও বলেছিলাম যে ইট স্লোজ ডাউন, অ্যান্ড কেন হয় সেটাও বলেছিলাম। ওকে, ইট ইজ দ্য সেম, মানে problem is this. Okay, it attains a terminal velocity. Okay, now what is this terminal velocity? Okay, so we'll just have Fm here in the opposite direction. So you know already Fm becomes mg when terminal velocity is attained. So Fm is bil mg. So I is epsilon by resistance R, say L mg. So it is B into epsilon is BLVT by R into L is mg. So we will get Vt as mgr by b square L square.